All right, hello everybody. So this is a continuation of the sort of recursion video there, where we're going to look at recursion on array-like things like strings and vectors and actual arrays like that. So you can actually use recursion on anything that has some notion of size, right? So as long as there's a way to sort of make it smaller, then you can apply recursion to that there like that. Of course, there has to be some, smallest sort of thing there that we can use as like our base case, but then we can use recursion. So we can use recursion on like strings and vectors and arrays and other sorts of like collections, but we have to be a little bit more careful here. So let's see what this looks like. So here's an example. Let's say that we want to write a function spaces, right? Where you give it a string and it returns the number of spaces in the string. So like this string here, hello, has 0 spaces, right? This string here has 1, 2 spaces, like that. And this string here has only 1 space in it there, like that. So it's a function that counts the number of spaces. And of course, you could do this with like a loop, right? That would not be hard. You'd have a counter variable. You'd loop through the characters in the string. If the character is a space, you increment your counter and you return the counter at the end there. Easy peasy. So to solve this recursively, right, we need to identify these sort of 3 key elements here. How are we going to shrink the problem? How are we going to make the problem smaller while still keeping it the same kind of problem? So when we did this with like integers, right, our sort of shrink tools were like n minus 1 or n divided by 2. But now we're working with a string. So we need to look at the operations that can basically like make the string smaller or get me a smaller sort of portion of the string. So we have things like pop back, or we could use like subster to get a copy of a sort of portion of the string, stuff like that. Then once we sort of settle on how we're going to make the problem smaller, we need to figure out what our base case is. Like what's the smallest form of the problem? And usually like that's kind of obvious. So in this case for strings, it's the empty string, right? If you have a string with nothing in it there, then like that's the sort of simplest and smallest like problem that we could have there like that. And then finally, we have to figure out how are we going to grow. So when we solve the smaller problem, right, when we sort of like take our original string and make it smaller, throw away one of the characters or whatever, we solve that smaller problem sort of by magic, right? The recursive leap of faith says that once you've shrunk your problem, you just magically get the correct answer to that sort of smaller problem there. But what we get is a small answer, right? We get an answer to the shrunk string, not to the original string. So then we have to figure out how do we take that smaller answer and grow it into the answer to the original problem, the original question that we were asking. So let's look at this for the context of strings. For shrinking, we can do a pop back. So just like vectors, strings have a pop back operation that removes the last character of the string. And that runs in constant time, so that's nice, right? We could use erase on the string. This particular one here of erase, like some index comma 1, will erase the ith character, just one character at a time out of that there. So for example, we could do erase 0, 1, and that would basically be equivalent to like a pop front. That would erase the sort of first character there. But erase is slower because a string is built on an array. So when we want to erase one of the characters out of the middle, everything after it needs to be shifted down to fill in the spot. So erase runs in O of I time. In particular, if we did this erase 0, 1, that would run in O of n time there, which is, not great, right? Both of those will modify the actual string, but subster does not modify the string. It leaves the original string unchanged, but it returns a copy of a portion of it, a substring. So S subster 1 would return a copy of the string with the first character removed. The original string is left alone, but the copy has the first character missing here. Or we could do S subster 0 length minus 1, and that would return a copy with the last character removed there. So it's kind of like a pop back, except that it doesn't actually modify the string. It just gives you a copy of the string that is what it would look like if you had done a pop back on it there like that. Subster runs in O of L time, where L is this thing here. It's the length of the thing that we're sort of asking for there. So in both of these, like that would be length minus 1, so that's basically like O of n for the two examples that I sort of gave here like that, right? So we'll probably prefer pop back, right? Because it's the fastest of the three, but the other two have their own sort of applications here. Okay, so we will use the string ABC as an example, which has two spaces, right? 1, 2. So the way we build this out is we say, okay, ABC has two spaces. This should return 2. We need to know what the function is like supposed to do there like that. So then we say, how am I going to shrink it? The shrink is over on this side, right? And we decided we're going to do a pop back. So the pop back is going to remove the character C from the original string, leaving me with a string that has one less character. So this string up here has a length of 5, and then this one here, right, has a length of 4. One less character there like that. Now, once I've made my thing smaller, I can apply the recursive leap of faith. Like the sort of magical recursion fairies that live in our computer will magically make this function call work, and it will return the correct answer there like that. So then we just need to ask, all right, what do I need to do on the way up? What do I need to do over here in the grow step there like that to turn the answer to the smaller problem into the answer into the original problem? And it kind of looks like the answer is nothing, right? Like what do I have to do to turn a 2 into a 2? Well, nothing, right? But that can't be right, because we're eventually going to get down to our base case down here, which is the empty string, right? And how many spaces are in the empty string? The answer is 0. Right? How many spaces are in the empty string? So something has to happen to turn that 0 into a 2. I can't just be doing like nothing all the way up here, or otherwise I would get not a 2 here, but a 0. So in reality, spaces has two different grow steps, two different things that we do on the way up there. So if the last character, the character that we just pop backed, right, is not a space, so like in the example we showed, it was the C in ABC, like that, then we do nothing, right? We take the number that we're given and we just sort of pass it back up the chain there like that. But if the last character is a space, then we add 1 to the result of what we got and then pass that sort of incremented value back up the change there like that. So you can see that if we just run this sort of thing one more step here, right? So if I start with my original string here and I do a pop back, that's going to remove the C like that. So now I have A space B space like that. But if I do it one more step here, that's going to remove that space there like that. So when I look at this string and the recursive leap of faith says that has 1 space in it. So what do I have to do to turn that 1 into a 2? I have to add 1 to it. I add 1 to it whenever the character that popback removes is a space. If popback removes a non-space, then you can think of it as like we just sort of add 0. So on the way back, I'm always adding something, right? I start at 0, and sometimes I do a plus 0, and sometimes I do a plus 1. So this is our implementation here. Our base case is if the string is empty. Right? That's this one right here. Like that right there. So if the string is empty, how many spaces are in the empty string? There's 0 spaces in the empty string there like that. And then I have 2 different recursive cases here. So my first recursive case is if the last character, s.back returns the last character. It's whatever character popback is going to throw away, right? So if that last character is a space, then we want to remove it, but on the way back up, we count it. We do a plus 1 on the way back up there. So that's recursive case number 1. And then our second recursive case is if the last character is not a space, right? That's the else off of this, so that means here s back is not a space. Like that right here. So we remove the last character again. We always remove the last character because we're trying to shrink it down to nothing there like that. But then on the way back up, we add 0 because it wasn't a space. So we don't want to count non-spaces. And of course, plus 0 doesn't do anything, right? You could take that out and just return spaces S like that, and it would do exactly the same thing here. I'm only doing that to kind of emphasize that, like, we either add 1 or we add 0, depending on whether the last character, the character that we threw away, was a space or not a space like that. So here's like the recursion tree for our sort of sample string here. So we're going to strip off the C, right? We're going to pop back the C, like that right here. And then we sort of keep track of, on the way up, we're going to add a 0. Then in the next one, we strip off the space. There's a space there, right? But we also keep track of, on the way back up, we're going to add a 1 because that was a space that we removed there. Then we remove the B, right? So B goes away. B is not a space, so we're going to add a 0 on the way back up. Then we're going to remove the next space, like that, right? So on the way up, we're going to add a 1. And then finally, we remove the A, right? The A goes away. A is not a space, so we're going to add a 0 on the way back up. And then we have the empty string, which gives us how many spaces are in the empty string? 0. So then on the way back up, we're doing the addition of, okay, 0 plus 0 is 0. And then that becomes the answer of how many spaces are in the string A. Then we do 0 plus 1 is 1. And 1 is the answer to how many spaces are in the string A space. So then this one becomes 1 plus 0 is 1. And that is the answer to how many spaces are in A space B. So then this one becomes 1 plus 1 is 2, right? And 2 is the answer to this one. 2 is the answer to how many spaces are in A space B space. So then this becomes 2 plus 0. And then finally 2 is the answer to our original question up here. How many spaces are in our original string there like that? Actually, hang on a sec here. One real quick thing, right? So is this linearly recursive or non-linearly recursive? It just goes straight down. So this is linearly recursive, right? But we're doing some stuff on the way back up, so it is not tail recursive, right? So in terms of the analysis that we're going to do next, right, the fact that it is not tail recursive means we're going to multiply the sort of base memory usage of the function, like whatever memory the function uses without the recursion, times the height of the recursion tree here. So we started with a string of length 5, and the height of the recursion tree is 1, 2, 3, 4, 5, 6. So the height of the recursion tree is the original length plus 1. Which basically just means the height, right, is O of n in the length there. So when we do the memory analysis, we're going to multiply the base memory times O of n there, like that. Likewise, the runtime is going to be sort of like the base runtime of the thing multiplied by O of n here for the sort of number of steps it takes me to go down and back up there like that. Okay. So yeah, like we were saying, it's linearly recursive, but it is not tail recursive. The height and size of the recursion tree, they're the same. They're n plus 1, where n is the length of the string there. So we just need to figure out what is the base runtime and memory usage of the function itself, ignoring the recursion, and then we multiply those by n plus 1 to get the actual sort of real runtime and memory usage there. So if you just sort of look at this function here, right? Let's do this, right? Haha, pretend that's not there. It's not there. You didn't see that. Like that, right? You might be like, oh, this is like a nice O of 1 function, right? Like we used pop back specifically because it's O of 1 there like that. Nothing I'm doing inside of the function is O of 1. But in fact, it is O of n. And that's because we're taking the string not by reference, but as a copy. So there is a hidden O of n operation in passing the parameter s. To get the string into the function here, we have to make a copy of it. And as we've seen from copy constructors, that involves looping over the stuff in the string there like that. So that takes O of n time, like that. It also takes O of n memory as well, though. So we're basically spending extra time and memory in here like that. So when we multiply it all out, right, our base runtime is O of n, but we multiply it by n plus 1, so that gives us a runtime of O of n squared. Then likewise, like we're stacking up a bunch of copies of the string with sort of less and less stuff in them there like that. So each step of the recursion tree adds O of n memory. So the total memory usage is also O of n squared there like that. And that's not great. Like if that was the way that recursion on strings and like vectors and arrays worked, like we would pretty much want to avoid recursion there. Fortunately though, we can do better. So usually when we're doing recursion on like something big, right, something where its copy constructor has to do like a loop under the hood there, we're going to pass them by const reference to avoid that sort of O of n squared that we have there like that. But if we pass it by const reference, then we can't modify it. We can't shrink it, right? So like how are we going to do that? So what we're going to do is we're just going to add another parameter, like an int or something, to keep track of how much of it have we looked at and how much of it is sort of still left to be processed there like that. So instead of literally shrinking the string, we will modify the int to sort of say, okay, I've processed an extra character, like now there's one less thing to sort of be dealt with there like that. And an int doesn't take like time to copy, right? Copying an int or a size t if you want to do that, right? That is just a linear time operation there. So that'll eliminate the sort of hidden O of n term. So we're going to modify our spaces to look like this. So our string is going to get passed as a const reference, and then we're going to pass this extra parameter I to basically keep track of how much of the string have we looked at here. So the definition of what spaces does isn't it counts the spaces in the string, it counts the number of spaces between position I and the end of the string there. So if I is 0, that counts everything in the string there like that. But if I is 1, it skips the first character. If I is 2, it skips the first 2 characters, and so forth. So we start I at 0, but the recursion is going to work by incrementing I, by moving I closer to the end of the string here. When I equals s.length, when I is like at the end of the string there, then that's our base case. That's where the number of spaces, like how many spaces are there between the end of the string and the end of the string? There's 0. There's sort of none there. So that will become our base case there like that. So here's the recursion tree for the sort of updated spaces here. I've highlighted the character that I is looking at. So this is I over here, right? So I is 0. We're looking at index 0. That's not a space. So we're going to add a 0. And then we increment I, right? The string is the same here and here. Only I changes. So now we're looking at the space that is there. That's a space. So in the next step down, we're going to add a 1. So because this is a space, we add a 1 down there. Now I is 2, so that means we're looking at B. B is not a space, so we're going to add a 0. Now I is 3, so we're looking at the space there. That is a space, so we're going to add a 1. Finally, I is 4. So we're looking at C, character number 4 in there like that. That's not a space, so we're going to add 0. And then remember the length of this string is 5. So when I is equal to 5, that is our base case where we return 0. And then on the way back up, we do the same thing that we did before, right? We're just going to add in these 0s and 1s until we get our sort of answer up here from 2. Notice that this version goes in the opposite direction, right? The popback one sort of worked from right to left, whereas this one, because I starts at 0 and we increment it, goes from left to right. Doesn't matter in this case like what direction you go, right? Because we're just counting spaces, so whether you count from left to right or right to left, you're going to see the same number of spaces. But it's a little bit interesting that it moves in this direction here. Because the new spaces is taking the string s by const reference, we're not copying it there. So the parameters, they don't take O of n time, they take O of 1 time. So inside of the calculation, right, that replaces the O of n with an O of 1. We have O of 1 times the height of the recursion tree. That's the height there, like that, is O of n. And then the memory usage is also O of n. And that's only because we didn't bother to make this one tail recursive. If we had made it tail recursive, then the memory usage would also be O of 1 there, like that, right? And the way we would do that is by adding yet another parameter to contain the sort of the space count on the way down here. We already have a parameter named S, so I would probably call it like maybe SP or something like that, right? So just add another parameter and do the additions on the way down instead of on the way up there like that. Wouldn't be too hard. We'll do a similar thing when we work with vectors, right? Instead of actually literally pop backing the vector or something like that, we'll have an extra parameter I that keeps track of which part of the vector are we interested in, which part have we not looked at yet, and which part have we already processed here. So we're going to write a sum function to sum the elements in a vector, but instead of summing the whole vector, we're going to sum all the elements between vi and the end of the vector there like that. So our shrink is going to be incrementing I, moving I closer to the end of the vector. Our base case is when I equals v size. Like, what's the sum of all the elements between the end and the end? The answer is 0. And then to grow, on the way back up, we'll add the ith element to the sum of the rest of the vector, the stuff that comes after it there, the stuff that the recursive call returns. So here's the picture for like the recursion on vectors, right? So here I is 0. So that means what's the sum of the whole thing? So if we sum 1, 2, 3, we get 6. If we add 1 to I becomes 1. So that means I'm interested in this part of the vector. I'm saying sum everything but the first element. The recursive leap of faith tells me, oh, that's 5, right? And then on the way back up, I add in the 1, which is what I is the index of, right? V sub I here is equal to 1. So you can think of like when we do the I plus 1, that kind of like removes the 1, like it removes it from consideration. So then on the way back up, we're going to add that sort of missing element back in there. Of course, if we keep, plus 1ing on I all the way down, eventually I will be equal to 3, which in this case is the size. Right? The size of this vector is 3. What's the sum of everything between the end of the vector and the end of the vector? The answer is 0. So on the way back up, we're adding in all the v sub i's for different i's, because all the different i's are sort of like, counting our way from 0 to the end of the vector there like that. So that's how we get the sum here. So the implementation is pretty short, right? We get our vector by const reference. I defaults to 0. Our base case is just if I is equal to v size, then the sum of that is 0. Otherwise, our recursive case is just add up everything else. Like that's what the recursive call is, just saying, okay, recursive fairies, please add up the rest of the vector, and then we just add in the vi that hasn't been incorporated into it again here. And again, this is linearly recursive, but not tail recursive. If you wanted to make it tail recursive, add another parameter like int s equals 0 to do the sum on the way down instead of doing it on the way up there like that, right? So if let's see, am I doing the analysis over here? No, I'm not. So let's do the analysis here real quick, right? So the time that it takes to get the parameters in is constant time. And then if we sort of ignore the recursion, right, and just look at everything else in here, the time taken to do all this is also O of 1 there like that. So the base runtime of this without the recursion is O of 1. Right? And then the height of the recursion tree is going to be the size plus 1 for the base case like that. So again, we get O of n, and that is both our runtime and also our memory usage, because we are not tail recursive there. If we made this tail recursive by adding the extra parameter and sort of doing that change there like that, that would reduce the memory usage to O of 1 there. All right. Now, what about arrays, like raw arrays here? Not like vectors, but like just like array represented as like literally just like a pointer to the beginning of the array there like that, right? So we can use the same trick. The only difference is we need another parameter to keep track of the size of the array so that we know when we get to the end. With a vector or a string, we can just do like, okay, dot length or dot size, but arrays don't track their own size. So we need another parameter to keep track of like what's the size, and then our base case will be I equals that. But because arrays sort of turn into pointers pretty easily, we can also do it a second way here where we can work entirely in terms of pointers using pointer arithmetic here. If you sort of need a bit of review on pointer arithmetic, I've got a separate video on that. So if you sort of like, wait, what's pointer arithmetic? What's it mean to add to a pointer? Go hit up that video there. Like, pause this one or whatever like that. But we'll sort of like look at these methods sort of over here like this, right? So here's two versions of the sum function modified to work on arrays here. So we're passing the array here, and when you pass an array to a function, that's exactly the same as passing a pointer. Like there's no difference between passing like square brackets to a function and passing just a plain old int pointer there like that. So we're passing the array, we're passing its size, and then we have an I which keeps track of, how much of it have we processed here. So again, our base case is if I equals size, we return 0. And then our recursive case is, okay, please add up the rest of the stuff here. So the array stays the same, the size stays the same, only I changes. And then once I've sort of gotten the answer to the recursive call there, I add in the missing array element, array subscript I. So the way that you would use this is if you have an array here, you would pass it to the function by giving the array and then the size of the array, the number of elements in the array there like that. And I defaults to 0, so I don't need to pass an I in that like that. So this is kind of like the array equivalent to the stuff that we've already done with strings and vectors. But the other way we could do this is with just a pair of pointers here. So start is a pointer to the first element of the array, and then end is a pointer to one past the end here. Right? So like in this array here, start points to 1, but end is technically beyond the end of the array here. It's sort of like the invisible spot that is 1 past the end of the array there like that. It doesn't point to 3, it points to the sort of thing that does not exist that is right after 3 there like that, right? So our base case here is if start equals end. Like if start has moved all the way over here so that it is at the sort of point beyond the end of the array, then there's nothing left, and we're just sort of finished at that point there. So we return 0 there like that. Otherwise, to shrink the problem, I'm going to move start one step closer to the end of the array by doing start plus 1 here. So start plus 1 doesn't modify the elements of the array, right? We're not touching the stuff in the array here. All it does is it moves the pointer from pointing to the first array element to point to the second array element here. I don't change end. End is sort of fixed at this sort of spot 1 past the end there like that. And then I add in, so star start is the number 1, or then in the next step it's going to be the number 2. It's the thing actually in the array at the sort of start position there like that. So both of these basically do the exact same thing. They add up the elements in an array. They just do it in a sort of couple of sort of slightly different ways there like that. The runtime and memory usage of both of these is exactly the same. It's still O of n for runtime and memory because these are linearly recursive but not tail recursive. So let's walk through this in kind of like in detail here using like a little memory diagram to sort of see like what's going on. So this is the second one. This is the sum that takes a start and end parameter that we're sort of looking at here. So I've placed the array in memory. So the start of the array index 0 is here at address 1000. The last element of the array, the 3, is at address 1002, but end is at address 1003. It's one step beyond the last array element there like that. So start here is 1000 and end is 1003. Now you might sort of be saying like, well, hold on a second here, right? I thought it was like, terrible to go beyond the end of an array like that. Like that's something that you sort of never want to do. And that's true, but you are allowed to have a pointer to 1 beyond the end of the array, you just should never do anything that actually tries to like modify the thing in that spot. So we don't want to dereference the end pointer. We don't want to ever do like star end there like that. But I am allowed to sort of like just have this address, have the address 1003 sort of, you know, in my possession. I'm just not allowed to say, hey, what's at address 1003? Because that address doesn't like belong to me there. That's sort of like an exception to the normal sort of like rules about like, you know, pointers is even though address 1003 does not technically belong to my program, like there might be something else in here that isn't like mine, I am allowed to sort of hold the address 1003 so long as I never like open it up and look in the box and try and see what's there. Okay, so we start off with sum being 1000 and end being 1003 here. So we are going to say recursively, all right, please add up everything in the rest of the array, like this part here, and then on the way back up, add in the 1. So the 1 is the star start here, right? That's that thing right there. Okay, so then we recurse again, and we say, okay, please, recursion fairies, add up everything in the rest of the array. So everything from 3 to the end, from 1002 to the end. And then on the way back up, we're going to add in the 2. So the 2 is the star start of this one. This one's start is 1001 there, like that. So we recurse again, right? Now we're saying add up everything from the end of the array to the end of the array. Start and end are identical. And then on the way back up, add in star start, which is 3. Now that those two are identical, we get our base case of 0. So then on the way back up, we're just adding up the things that we have here. So this here, what's the sum of the end of the array to the end of the array is 0. That becomes 0 plus 3. So that's 3. And that's going to be the answer to this one. So this is 3. 3 plus 2 is 5, right? 5 is the answer to this one up here. So this becomes 5. 5 plus 1 is 6. And 6 is the answer to my original question up there. What is the sum of the entire array there, like that? So start is kind of like, you know, walking through the array, pointing first to the first element, then the second element, then the third element, and then it hits the end of the array. And then on the way back out, we're just adding up the stuff that we sort of saw on the way down there, like that. Like I was saying, right, in C++, it's legal to construct a 1 past the end pointer, but we never dereference it, right? We're never doing star end, because then we would be saying like, hey, what's in here? Like, what's there? And that spot does not technically belong to me. So this is a little aside here, right, of like how this applies to vectors here, right? So for sum, right, we can write it two different ways to work on arrays. We can do the size and index version, or we can do the version that we just looked at with the 2 pointers there, like that. But for vector, there's really only one version here, which is we pass the vector by const reference, and then we use I like that right there, right? We can actually use the first two sums on vectors as well. Like these two can be applied to a vector if we access the backing array, the sort of array that is in the background behind the vector. And you do that by doing .data. So if I have a vector v, I can do v.data, and that gets me the array or the pointer that is in the background behind that that vector there, like that. So I can use these two functions up here to work on a vector. I just have to sort of turn it into an array. Using .data doesn't make a copy of the vector or anything like that. It's just giving you access to the sort of underlying array there, like that. So this would still have the exact same runtime and memory usage there, like that. So like of these sort of like three possible implementations, right? The array versions are more general because they work on arrays and vectors. The vector version only works on vectors. There's no way to sort of like take an array and apply the vector version to it without literally copying it into a vector there and using extra memory. The sort of modern C++20 way to work with both vectors and arrays is to use this thing called a span. So a span is kind of like a vector that doesn't own the array. So it has like an array in the background, but the array doesn't belong to it. So you can wrap up a vector or an array or anything that sort of looks like a vector or an array there like that. So here we're passing in a span like that right there. If the span is empty, we return 0. Otherwise, we take the front of the span and then we add that to the sum of everything else. So we're getting a subspan here, which is like everything after the sort of first element there like that, right? So the fact that like there's no reference here looks like we're going to be in trouble, but in fact a span is actually a small thing. A span is not a vector, it's not an array. Copying a span does not involve copying a bunch of stuff here. Copying a span is cheap. It takes O of 1 time there like that. So this is kind of like the more sort of modern way. This will work with both a vector and also with an array there like that. I'm not going to use this, but I did kind of want to show you, right, that there is like a sort of built-in way that we can build a nice recursive function that sort of like, you know, works easily, doesn't require me to think about pointers and stuff there, and it will work with both vectors and sort of raw arrays there like that. But I'll stick with like the sort of raw pointer stuff there or raw arrays for recursion purposes, just because you're probably more familiar with them. I don't want to do a whole lecture just on the sort of standard library span class there. Okay, so for summation, right, it doesn't matter whether we sum from the front or the back, right? So we could make a modified version of sum. This is the OG sum right here that works forward, right? It starts at the beginning and goes forward like that right here. But we can also make over here, this version of sum starts at the end and works backwards. So the base case is the same. If start equals end there like that, we're going to return 0. But we're going to modify end. We're going to do end minus 1 plus star end minus 1 here. The minus 1 is necessary because remember, end is always 1 past the thing we want. So if when we're looking at like, you know, a particular endpoint, the element of the array that we're interested in is actually 1 before that there like that. So this version here works by pulling end towards the beginning of the array, towards start. Whereas this one over here works by pulling start towards the end of the array there. Because it's a summation, of course, it doesn't matter, like, you know, it doesn't matter what order you do addition in there. So like it's going to work the same whichever way you sort of want to do it. But it's a little bit interesting that you can work in both directions there. All right, let's do another one here. Like, let's say we want to write a function find, right, that takes a vector and returns the index in the vector at which x exists here. So we're going to add a sort of hidden parameter onto the end here, I, which is going to default to 0, and that's basically going to keep track of like how much of the stuff have we sort of looked at so far here. So if we do a find for 1, right, so this is the thing we're looking for, the first occurrence is at index 0, so that returns 0. If we do a find for 2, there's only 1 2 in here, so that's going to return index 1. And then if we do a find for something that does not exist, it returns the size of the vector, which means like it's not found. It doesn't exist in there. Okay, so how do we break this down, right? Our base case, we've added the sort of invisible I over here like that. So our base case is just when I equals v dot size. That's we're saying like, all right, search between the end of the vector and the end of the vector. Well, there's nothing there, so we're just going to return v dot size to mean, okay, whatever you told me to look for, I can't find it because you didn't give me anything to search in there like that. Our other base case is if the ith element of the vector is equal to x. Then we found an x at index I, so we're going to return I. And then the recursive case is if vi is not equal to x, we need to search the rest of the vector. So we will increment I by 1, right? And then whatever that sort of recursive search finds, we will return that. So here's an example of like sort of the two cases here that ends in the sort of two base cases. So here, this is if it is not found. We're looking for a 7 in this vector here. There's no 7s in there, right? So we check the sort of like first element here like that, and we say, is that equal to 7? No, it's not. So we do I plus 1, and we say, okay, check the rest of the vector. Check everything from 2, 3, 1 to the sort of end there like that here. Now, the recursive leap of faith takes over and says, if you ask me to find a 7 in 2, 3, 1, I won't. There is no 7, so I'll get the correct answer 4 for that. And then on the way back up, we just return what we're sort of given there like that. The base case is when I is all the way at the end, and I ask you to search between like sort of nothing, and there's nothing there, so of course I can't find it there like that. The other base case is if we find it. So for example, like let's say that we tell it to look for a 2. So where's a 2? There is a 2, excuse me, we're telling it to look for a 3. Sorry, I was mixing up my numbers there. Like 3 is the thing that we're looking for. Where's there a 3? There's a 3 at index 2. So that should be what we expect to get out here like that. So initially, let me erase this stuff up here, right? Like that. So initially we are saying search the whole thing, like that right there. Well, that's what I equals 0 means. The first element, 1, is not equal to 3. So we're not going to sort of like stop yet, right? So the recursion increments I, which means, okay, now search this section there like that, right? The recursive leap of faith tells me that we're going to get the correct answer here, but if we just go one more step beyond that, we'll literally see why we get the correct answer here. So 2 is not equal to 3, so the recursion is going to proceed on to this next step here. So when I is 2, right here like that, we hit our second base case. This element here is equal to the 3 that we're looking for, so we return the current I. The current I is 2. We return that, and then we just sort of pass that up the chain unchanged there like that. So we have a base case if we get to the end, and then we have a base case if we're not at the end, but we find what we're looking for there. And the recursive case is basically just like, okay, move forward. So here's our implementation here. Base case number 1, if we're at the end, that the only way that I can get to the end, right, is if I didn't already find the thing, so we return size to mean not found. That's the not found base case there like that. On the other hand, if I'm not at the end, but vi is equal to x, then that means I found it. So this is the found base case. Where did I find it? I found it at index I, so I return index I. And then this one here is the recursive case where it's like, I didn't see it here, but I'm still going to continue searching the rest of the stuff. So v stays the same, x stays the same, and I gets incremented to I plus 1 there like that. Right. So is this linearly or non-linearly recursive? There's only one recursive call here, so this had better be linearly recursive. And then if it's linearly recursive, is it tail recursive? Well, nothing happens between the recursive call and the return, so this is tail recursive. Like you can kind of see that in the previous slide here. Whatever answer we get, we just pass it up unchanged here. So this one is, in fact, tail recursive and linearly recursive there like that. Which means if we sort of like, we do the analysis here, right? We're passing a const reference, so our parameters take O of 1 time like that. All the stuff that we're doing in here is O of 1 time there like that. So our runtime is going to be O of n, because the recursion tree is going to have height n plus 1, but our memory usage is going to be O of 1 there like that. So that's nice. Like that's basically the same as the sort of loop-based version that you could write for this one here. Now find starts at the beginning and searches forward. So it's going to find the first occurrence of the x that you're sort of telling it to look for there like that, if x occurs more than once here. We can also do a reverse find, an R find, that starts at the end and looks, sort of goes in the opposite direction here. So it's going to find the last occurrence if there's more than one here. So if we tell R find here to look for the number 1, it's going to find this one, the one closest to the end there like that. If there's only one, like there's only 1, 2, right, then R find and find give the same answer. And of course, if the thing you're looking for doesn't exist at all, we still get out v.size like that. So they only differ if there is more than one copy of the thing that you're sort of telling it to look for there. So the question is, can we write rfind recursively here? There's a couple of ways you could do this. One way you could do this would be just to start I at the end and decrement I instead of incrementing it there like that. You can do that, but you need kind of like a helper function to get I started at the end there. I can default I to 0 easily enough, but I can't default I to size minus 1. I would need another function to call it with I being size minus 1. But an interesting problem is, what if we don't change the way I works, right? So I is still going to start over here at 0 and move towards the end. Can we still do an R find and find the last occurrence of x while moving from beginning to end here? And the answer is yes, we can. So our first base case doesn't change. If we get all the way to the end and I didn't find an x, right, then that means there aren't any. So we return v.size to mean not found. Now, what was base case number 2, where v sub I equals x, that's going to become a recursive case here. So if we see an element of the vector that is equal to x, we found an occurrence of x. Like we found an x, but we don't know if it's the last one here, right? There might be more later. So what we do is we do the recursive call to check the remainder of the vector and then check what it gives us here. So if the recursive call gives me v.size, that means there were no more x's. That means not found, right? So if there are no more x's in the rest of the vector, then this is the last one, and we return I here. On the other hand, if the recursive call does not return v.size, that means it found a later x, and we want that one. So we return whatever the recursive call gave us there, like that. So there'll be like a kind of like an if-else, or I think I wrote a ternary operator inside of this recursive case to basically check the result of the recursive call here. And then the second recursive case is just identical to the sort of other one here. If vi is not equal to x, then just is like, okay, search the rest of the vector. So this is the implementation of this thing here. This is the base case. That did not change. If we get all the way to the end, then I couldn't find what you were looking for, like that. This one here, this is where the big change is. This used to be a base case if v sub I is equal to x. Now it's a recursive case here. So what we're going to do is I found an x, but there might be more. So I recursively search the rest of the vector, right? I do I plus 1 to search the rest of it there. And that gives me an index j. Now, if j is v.size, that means there were no more x's. So this one, the one at index I, is the one that we want there. On the other hand, if j is not v.size, that means I found a later x, and I want that one. So the two possibilities here are like we're at index I, here's an x, and then we searched the rest of it. So if j is over here at size, that means that there are no x's in that section there, like that, right? On the other hand, if x is here, right, and j is here, that means there is an x there like that, and we want that one. So we're not going to, instead of returning I, we're going to return j in this situation here. And then the final recursive case is just exactly the same here. It's like, okay, if this isn't an x, I don't care, like continue to search the rest of it there like that, right? This one is not tail recursive because we have to do the check on the j sort of variable there after the recursive call returns here. So this one is not tail recursive. That means it's going to use O of n memory. There is a way to make this tail recursive. There's almost always a way to take a linearly recursive function that is not tail recursive and make it tail recursive, and it probably involves adding an extra parameter onto it here like that. But in this case, it's not quite as easy or obvious as the other ones there like that. So here's like a picture of this working, right? So we are looking for the number 1, that is x there like that, and we're starting at index 0, that is I. So v sub 0 equals 1. So that means, hey, I found a 1 here, but I want to check and see if there are any other ones in the rest. So then we do a recursive call here. This rfind here is saying, find me a 1 in the rest of the array there like that. And we find another one, right? Like v at 1 is 1 here like that. So I have sort of two candidates. I have this one and I have this one there like that, right? Then we search the rest of it because we don't know. There might be more 1s over here, but there aren't. So that gives me a 4 telling me that there are no 1s in like this section, the section 2 and 3 there like that. So here j equals 4. So we check 4 equals v dot size, and that is true. So that means we want 1 here, right? This one is the last one in the rest of the array there, like that. Then up here, we check to see is 1 equal to v dot size, because we have 2 candidates. We have either position 0 or we have position 1. If 1 was not 1 but 4, that would mean there were no x's, and the first one is the only one there, like that. But it's not. It's a 1 here. So basically 1 is greater than 0, so we're going to return 1 and not the 0 that we get there, like that, right? We're basically returning the sort of largest non-v dot size index that we find as part of this sort of search here, like that. All right, so let's sum up here, right? So we can do recursion by actually shrinking, by doing popbacks and stuff like that. Doing so requires copying, and that sort of like multiplies everything, both memory and runtime, by O of n there. So for the stuff that we've looked at, like that will lead to sort of O of n squared work like that, which we want to avoid, obviously. So usually we'll add an extra parameter like the I or whatever there, like that. Sometimes we'll need more than one, but like at least one there, like that, and we'll leave the string or the vector as const reference. So the recursion will happen by like incrementing or decrementing I there, like that. If we're using like arrays and pointers here, then you can just do the recursion on the pointer directly. You don't need an extra parameter because we can modify the pointer without making a copy of the whole thing there, like that. All right, that's it for like recursion on strings and array. We'll apply recursion to some of the stuff that we're sort of looking at going forward. But if you want at this point, you can jump into the sort of sorting algorithm stuff.